Hi, in this series, I'll be giving an introduction into ordinary differential equation and show you techniques into solving first order linear and second order linear equations. So let's begin with an introduction into ODEs. So what are ODEs first of all? Well, first we have to ask what is a differential equation. And that is basically an equation involving derivatives. Examples you have already seen in class, like just differentiating dy dx equals to 1 or x squared. This is already a differential equation, but it's very simple. In this case, where dy dx may be equals to x squared, you just need to integrate both sides to get y equals to x cubed over 3 plus a constant. And that's what is usually done when you have only x terms on your right hand side. So the reason why differential equation is so important is we realize that in everyday life, physical processes can be modeled using this differential equation. Examples will be the motion of objects falling near sea level. So in this case, we know that by Newton's second law, F equals to ma, but the acceleration can be written in differential form, which is dv dt. And in that case, with the force of gravity being F equals to mg and the air resistance being F equals to gamma v, which are just some terms, we just know that this net force must equals to the downward force minus away the upwards force, because the ball is falling down. So of course down is larger than up. And because g is this, and we take some constants to fill in, then we get this differential equation dv dt equals to 9.8 minus 0.2 v. So this is an example of differential. But instead of having only t on this side, we realize that this side now has a v, so we cannot just integrate with t. It's because here you can't integrate with t because this is a v. So that leads us to finding techniques to solving this type of equations. So more terminologies that we need to build upon first is what is known as a direction field. So instead of finding the explicit solution to this equation, we can actually plot this dv dt over v. And this allows us to find the direction field of the solution. So how do you find the direction field? Is basically you just submit different v's and you get different gradients. And what is a gradient? The gradient is just of the gradient. This dv dt value is the gradient of the tangent line of the curve. So maybe at, let's say, a point 45, then all the direction will just look like that. So along this horizontal line, all of them will look like the same gradient, because this is just in terms of v lah. So if it has t inside, then you just need to find the different gradients at different points, and then you can plot the direction field of the differential equation. And this is really important as it gives us the behavior of the solution when you cannot find the solution explicitly. So along the horizontal lines, horizontal solution curves, meaning let's see at 50, then so let's say we take the previous example over here. Equilibrium solutions are basically when you let your dv dt equals to 0. So meaning why we call equilibrium is because when your dv dt is 0, it means the rate of change is is 0, meaning it's constant. That's why it's equilibrium. So it's constant. So there's no change actually. So dv dt equals to 0. You find that your v is 49. Meaning at 49, the gradient is 0. So everything is, this will be an equilibrium point, equilibrium solution. So it's just a straight line, straight horizontal line. Then everything above it is decreasing, and everything below it is increasing. And you can actually find the direction curve and see that if you start from here, you'll be going this way. If you start from here, you can just plot out to go this way. So that's basically how you understand the solutions. That's why direction field is so important. Now we move on to actually learning what are the different types of differential equations. So we have an ordinary one, which is what we'll be studying in this course. And an ordinary differential equation just means we have only one independent solution. And partial differential equation just means we have more than one. So examples of a differential equation, ordinary one, will be just this. You see, everything is in terms of, we differentiate with respect to only t. But maybe a partial one will be the following, where we differentiate with x and differentiate with respect to t for this function u. We can also get a system of differential equation. So your dx dt equals to some terms and dy dt equals to some other terms. And the order of a differential equation is just the highest derivative appearing. So if you just take this example, this is a third derivative plus 2et times second derivative plus y times first derivative equals to t4. So the highest derivative here is the third derivative. So we say it is a third order differential equation. Now, we again classify certain differential equation into linear and non-linear. And what does it mean to be linear? It means it is linear in terms of, so this function will be linear in terms of the variables of y. So t can take on anything. So in this case, t is like your constant. So it doesn't matter what it takes on. It will always be like, even t4 is a constant. When you talk about the differential equation being linear, it has to be linear in terms of the y terms. And thus a general linear ODE will look like some function t times y plus all the way to ant times y equals to gt, and g can be anything. So your coefficients are in terms of t and they can be anything, but your derivatives and your y terms must be all in the power of 1 only. And if this constant t, the gt, is 0, then we say the ODE is homogeneous. Otherwise, it is non-homogeneous. And if the equation doesn't look like that, then it's non-linear. So, for example, earlier we see that we have this, and this can't be linear because the y and the y is multiplying with the first derivative, so it's non-linear. So this differential equation is linear. And how do we do it? Well, we learn from calculus. What we can do is recognize that we can divide this over, and then this, when we integrate, this dt will be removed and it will be like integrating with respect to p only because of the chain rule. And so the other side now, because it's a constant, you just integrate normally with respect to t. And then when you solve it, you get to, this is just ln modulus of p minus 900 equals to 0.5t plus c. Then you bring the power of e up, and then you remove the modulus, And then you recognize one thing. You recognize that e to the power of big C is just a constant. And actually, so this part when you split, this part is just a constant. And you can label it A, which is what I do. But in the notes, we label it small c. And this is just the solution of the differential equation that we already can find using calculus. So this is one of those simple cases, and we'll later classify such cases. So because it has a constant, right, you can actually tell that there will be infinitely many solutions to an ODE one. Because when you integrate all these constants that you have, they will be part of the solution. So you can really there will always be infinitely many solutions. And the graphs of this solution are just called the integral curves. And sometimes, while a differential equation has infinitely, there are certain constraints in the context of the mode of the question that has an initial condition for us to solve such a solution curve. So let's say it starts from here, then it must follow a trajectory down. And what we know, for example, in this case, we just say that P0 is 850, meaning the initial population of this mice is 850. And then we can find the C is minus 50. So this is the solution. And the definition will then be given as, if an initial condition is given, then the ODE with this initial condition will be known as an initial value problem. And a function that satisfies an ODE is called a solution if it satisfies the equation. And the collection of all solutions is known as the general one, meaning this is a collection of all because it is the C. So the collection of all is just this set running C through real numbers. And the solution of a specific IVP is then known to say is the solution to the IVP if it satisfies the initial condition. So when a solution to an equation is like we found in algebra, like maybe x squared plus x equals 0, a solution to this expression is finding an x such that this holds. So similarly, a solution to an ODE is finding a y which has to be a function such that this holds now. So these are all the basic terminologies that we start off first. So this is like the intro course. I hope you have enjoyed it, and we'll dive deeper into different classes of ODEs and how to solve them. I'll catch you in the next video. Bye!